Hello everyone. The title of this video is Solve Similar Figure Applications. All the exercises from this video are taken directly from a free online textbook at openstax.org, and I'm in their Intermediate Algebra 2nd edition text, and I'm in section 7.5 titled Solve Applications with Rational Equations. And the exercises I'll be doing in this video are under the heading Solve Similar Figure Applications. So I'll be working on exercises 275 all the way through 284. So that is 10 questions. Examples 1, I'll label them examples 1 through 10 in the video. Alright, so example 1 will be exercise 275, example 2 will be 276, and so on until example 10, which will be 284. I will also have timestamps for when each example begins in the description of the video. So if you'd like to look at any particular one, you can just jump right to it. Alright. So I'm just going to start with this first one. Now in the first several exercises, we are told the triangles are similar. And I'll talk about what it means for two figures to be similar. And knowing that they are similar, we're then asked to find the length of the indicated side. Alright, so exercise 275, example 1. So I did my best to draw the pictures by hand. And again, we are told that these triangles are similar. So let me talk a little bit, before I get back to this problem, talk about similar figures, similar polygons, usually is what we're working with. And in our particular examples, we're going to be working with similar triangles. Alright, so two figures are similar if they have the same angle measures, if corresponding angles are congruent. Right, corresponding angles are congruent. Congruent just means, congruent angles just have the same measure, right, the same number of degrees or radians or whatever you're used to. So here, the way that they're laid out, they didn't give us any similarity statement. So I'm thinking that they're laying these out so that corresponding angles are in the same position. So what I mean by this is that, angle A in the lower left of this triangle has the same measure as angle X in the lower left of this triangle. So I put a little arc mark, right, one arc mark to indicate that these two angles are the same angle, same measure. They're both like 30 degrees or something, right? And then the angle on top, right? Again, the way these are laid out, I'm guessing that, they set it up so that angle measures in the same position are corresponding to one another. So the angle on top of this triangle, angle B, right, which I'll put two arc marks on, should be the same measure as the angle corresponding to it in this other triangle, this similar triangle. So angle A would correspond and be congruent to angle X. Angle B would be congruent to its corresponding angle, angle Y. And then the lower right angle, right, which I'll do with three arc marks, angle C in the lower right of that triangle should be congruent to angle C in the lower right of that triangle. So in similar figures, corresponding angles are the same measure, are congruent, And here's the big one. All right, here's the big one, the one we're going to set up proportions with. Ratios of corresponding sides. Right, ratios, fractions, right? Ratios of corresponding sides are equivalent. All right, and this is the big one. So again, if the way these are drawn, if they've put the corresponding stuff in the same positions, so A corresponds to X, B corresponds to Y, C corresponds to Z, then the following ratios would all be the same. Again, if they are similar, what they said they were. So the length of AB, right, the length of segment AB in the big triangle divided by the length of its corresponding side. Now AB is in the same position as XY here, right, in the smaller triangle. So this ratio should be equal to any other ratio of corresponding sides. Right? The ratio of any pair of corresponding sides will always be the same in similar figures. So AB divided by XY should be the same ratio as BC divided by, and then BC's corresponding side in the other triangle is YZ. Right? But not only are these equal, but both of these ratios should be equal to AC over XZ as well. Right? All three of these ratios, the ratio of every pair of corresponding sides, are the same value, are equivalent, if the figures are truly similar. Now notice in every single one of these ratios, my numerators and denominators were consistent. Right? You see how all the numerators, these come from triangle ABC. And all my denominators are also consistent, right? All the denominator side lengths, the XY, YZ, and XZ, these come from the same triangle as well. And you've seen this, right? When we set up proportions, when we set fractions equal to ratios equal to ratios, fractions equal to fractions, I want to set things up so the numerators are coming from the same place and the denominators are coming from the same place, right? That way we're staying consistent. Right? It was very similar to how when we set up proportions with units involved, I wanted the units of the numerators to be the same and the units of the denominators to also be the same. So I'm remaining consistent. Alright, so this is what it means for figures, not just triangles, but any figures to be similar. Corresponding angles are all the same measure, and the ratios of corresponding sides are equivalent. And again, this is the one we're going to use, this idea here. The ratios of corresponding sides are equivalent. So now in part A, right, in part A of this exercise, we are asked to, let's look this up. In part A, we're asked to find the length of side X. Right, find side labeled little x. Well, that's in this picture, little x is the length of YZ, right, segment YZ. And this side YZ, right, this corresponds to BC in the bigger triangle. Right. So I'm going to set up, I'm going to use this concept that in similar figures, ratios of corresponding sides are equivalent. So I'm going to set up a ratio at YZ over BC, and this ratio should be equal to some other ratio of corresponding sides. Now notice here, in the numerator, I have a side from triangle XYZ, and in the denominator, I have a side from triangle ABC. So on the other side of the proportion, I would like the same thing. I'd like a numerator from triangle XYZ and the denominator to be from triangle ABC. And I want to set it up so that this proportion has only one variable, little x. So I can't use AC, right? Length AC has little b. I don't want two variables in the equation. So I've already used BC, so that means I want to use AB then. Right? So on the other ratio, on the other side of the equal sign, I'm going to use side length AB, and again notice I'm putting that in the denominator because it is also from triangle ABC. And side AB corresponds to side XY from the other triangle. And then fill in the information. Right? Length of YZ is X over length of BC, its corresponding side in the other triangle, is 9. And this ratio, right, if they're similar, should be equal to the ratio of XY, which is 10, to AB, which is 15. And then we are solving this proportion that is set up. Right? Solve this proportion. Alright, now this is pretty simple. Now, first off, I like simplifying the fractions if they can before going into solving the proportion. So left side still little x over 9. And then 10/15ths, they have a common factor of 5. That reduces to 2/3. And then, the LCD here would be 9. I would simply multiply both sides by 9. On the left side, the 9's would cancel, leaving me with x. On the right side, 3 goes into 9, leaving a factor of 3. 3 goes into 9 3 times. So I have x on the left equals 2 times 3, which is 6 on the right. All right. So if these triangles are truly similar, as they said, then the ratio, 10/15ths of those corresponding sides, that's 2/3, should be equal to the ratio of these corresponding sides, right, YZ to BC, and isn't 6 to 9? 6 over 9 is the same as 10 over 15. They're both 2/3. So this is a valid answer for that side length, right, if the triangles are similar, the ratios of corresponding sides are similar. Great. Alright, then part B is same thing, but just the length little b here. Right. In part B, same picture. We're asked to find the side with length little b, which is side AC in the big triangle, right? Triangle ABC. And side AC, corresponds to side XZ in the other triangle. So that'll be one ratio I put up, the ratio of those sides, AC to XZ, and that should be equal to, any other ratio of corresponding sides since they are similar figures. And once again, I want the numerator to be from the same triangle as AC, and the denominator to be from the same triangle as XZ. Now this will be little b over 8. So I want the other side to have no variables, right? I want the only variable to be little b. Alright, so I can't use, now you could use 6, right? But let's say I didn't find 6 yet. I want to use xy then, right? I'm going to use xy in the other triangle. And notice I'm putting that in the denominator, right? Because it's in the same triangle as this denominator. And xy corresponds to AB in the triangle ABC. And now the proportion, fill in the information. AC has a length of little b. XZ has a length of 8. And then AB is 15 over XY is 10, which is 3/2 when you reduce it. Right? And then I would just multiply both sides by 8, Right, this side by 8, and then the 3 halves by 8. 8's cancel over here, leaving me with b. 2 goes into 8 4 times, so I'm left with 3 times 4 is 12. B would have to have a length of 12 units. I'll put that back in the figure. And again, let's make sure that this makes sense. Let's check. You know, if these are really similar figures like they said, the ratios of corresponding sides should always be the same. So 15 to 10 is 3 over 3 halves, 9 to 6 is 3 halves, 12 over 8 is also 3 halves. Right? The ratio of every single pair of corresponding sides here is 3 halves, so this works for little b. Okay? So this should be pretty simple. All right. So I'll go over the next examples a little more quickly. All right. I'm not going to be drawing pictures anymore. All right. I'll just show you the picture on the website. Okay, so next example, example 2, which is exercise 276 here. Same pictures, or well, it's the same, not the same picture, but it's the same type of problem. I'm given 2 triangles, and I'm told that they are similar. I'm not told how, so I'm going to assume that, D corresponds to N, E corresponds to P, and F corresponds to Q. All right, I'm going to assume that based on this picture. All right, so let me pull up the website. So you see the picture in the upper left corner of the page here. And I'll pull up some new paper. This is example 2. Hopefully you can see my writing. And look at part A. All right, part A, we're asked to find side little d, right, the side length of little d. Now in the picture, little d is over here in triangle DEF. That's side length E to F, right? That's side length EF. And EF corresponds to, so the ratio of EF to PQ, right? EF in the left triangle corresponds to PQ in the right triangle. So I have the ratio of EF to PQ, right, should be equal to the ratio of another pair of corresponding sides. And I'd like the numerator to be from triangle DEF and the denominator to be from triangle NPQ. And I want to set it up so that little d is the only variable. So I don't want to use little q, that means I don't want to use pn. So I have to use nq from that triangle, and that's going to go in the denominator on the other side. And then nq corresponds to df in the triangle DEF, right? So I have this proportion. All right, and I'll make this a little bigger. And we start filling in the information, right? EF was little d. The length of P to Q was 11 halves. Right, so what I have over here is a complex fraction, right? Fractions within fractions, but it's very simple to simplify this. Right, equals, and then DF had a length of 7. NQ has a length of 9. Right. Now you could just multiply both sides by 11 halves here. Nothing wrong with that. Or, if you want, this complex fraction over here we can simplify by multiplying the numerator, everything above the main bar and below the main bar by 2. And that'll cancel these 2's down here, leaving me with 11. So I have 2d divided by 11 equals 7/9. Alright, and then if you want to do the LCD stuff, go ahead. Multiply both sides by 99. That would be the LCD, and then 11 goes into 99 9 times, 9 goes into 99 11 times. And I've got 18d, right? 9 times 2d on the left, and then equals 7 times 11, or 77 on the right, and then dividing by 18. Get the length of little d is 77/18. And that doesn't reduce any further, right? This is 2 times 9, or 2 times 3 times 3. 77 is 7 times 11. There are no common factors. So this is the length they're asking for, 77/18. And you could check that, just go back to the equation here. Is 77/18 divided by 11 halves, or 2 times 77/18 over 11, does that equal to 7/9? And yes, it would be. I'll leave it to you to check. I'll put a little check mark, remind you, check your solution. Okay, then part B, number 2, part B here, similar problem, right? Similar question. Find side, the side with length little q. And little q is the length of side PN, or NP. So we take NP and divide that by its corresponding side in the other triangle, which would be DE. And this should be equal to, some other ratio of corresponding sides. I'll use DF and NQ again. So now this time though, I'm going to have NQ in the numerator and DF in the denominator, because I want, the numerators to come from the same triangle and the denominators to come from the same triangle, right? Remain consistent. Alright, then making this a tad bigger. NP, that's the little q. DE is 5 halves. So again, I have a little complex fraction here. Equals, and then once again, this is 9 and 7, so 9/7. Now the much easier way to do this is, just multiply both sides by 5 halves. Right, because here I have q divided by 5 halves. So multiplying by 5 halves gets rid of that 5 halves. And I do the same thing on the other side. Take 9/7 times 5 halves, and we get q alone equals, and nothing really cancels here. This is 45/14. And that's it, right? This is 2 times 7. This is 3 times 3 times 5. There are no common factors. And then check it, it should make that ratio true. Should make this proportion true. So yeah, you could simplify the complex fraction, multiply the numerator and denominator by 2 to make it 2q over 5, and then, do it the long way, but, I'm seeing a little shorter way here, so I decided to do it, and there's nothing wrong with that as long as you're doing proper steps, right, actual math. Okay. So next question. Now in the following exercises, right, after this, when we get into 277, 278, use the map shown. On the map, New York City, Chicago, and Memphis form a triangle. The actual distance from New York to Chicago is 800 miles. And then they ask us to find the actual distance from New York to Memphis. Alright, so you see on the map here, right, suppose we're looking at a map, a road map, which, like, what is that? Anyway, you're looking at a map, and then on that piece of paper, that map from Chicago to New York is 8 inches on the map. From New York to Memphis is 9.5 inches on the map, on the piece of paper. And Chicago to Memphis is 5.4 inches. Right, that's what the little double marks mean. And we're asked to translate these to actual distances. They tell us New York to Chicago is actually, 800 miles. So then what would be the distance from New York to Memphis and Chicago to Memphis? All right. So I'll actually draw another picture here and come back with this example. All right, so what I've done here is drawn 2 pictures. Same triangle. I know it's I did a hand drawing, it's not perfect. One's the triangle you're seeing on the map, right, where it's 8 inches from Chicago to New York, and 9.5 inches from New York to Memphis, and 5.4 inches from Chicago to Memphis. The other triangle is the actual triangle, the actual distances in real life outside the map, that you would have to travel. From Chicago to New York, they told us that was 800 miles. Now, just like any other application, if anything is unknown, call it something. Pick a letter. So from New York to Memphis, I don't know that distance in actuality, so I called it X miles. And then from Chicago to Memphis, again, I don't know that actual distance, so I'm going to call this Y miles. And these should be similar. This triangle is similar to that triangle because these vertices of the triangle correspond to the same places, right? These should have the same shape, just much different sizes, right? Inches to miles. Same shape, but different sizes, much different sizes. But they should be similar figures. All right, so part A, example 3, exercise 277. Find the distance from New York to Memphis. All right, so I'm going to set up a proportion here, right? If these truly are, and they should be, similar figures, similar triangles, then the ratios of corresponding sides should be the same. So look, on the actual triangle, Chicago to New York is 800 miles. And that corresponds to the distance from Chicago to New York on the map, which is 8 inches. Now I'm going to put 8 inches, the word inches here, right? So 800 miles in real life is represented by 8 inches on the map. And this ratio of corresponding sides should be equal, throughout the entire problem for both these figures, for any pair of corresponding sides. So we want from New York to Memphis, which I called X miles. And notice again, I have miles in both numerators, right? Both these numerators are coming from the same triangle, and the denominator is coming from the same triangle as well. Now, from New York to Memphis in actuality is X miles. I don't know that. From New York to Memphis on the map is 9.5 inches. Same units in the denominators. So we're solving the following proportion. Right, I have 800 over 8 equals X over 9.5. Now, bring this over here. Right, 800 divided by 8 is simply 100. Equals X divided by 9.5, and I can just multiply by 9.5. And when you multiply by 100, that just moves the decimal place to the right twice, right? 9.5 times 100 would be 950. So replace X with 950 in the map here, in the actual map, the actual triangle. And there we go. There's the distance from New York to Memphis, 950 miles. So that's the number, that's example 3, number 277. And then it would be a very, very similar setup for example 4, which is exercise 278. Find the distance we want from Chicago to Memphis. Well, you can probably see that it's going to be 540 miles, but again, Chicago to Memphis, that's, Y miles. In real life, I don't know that. And that corresponds to Chicago to Memphis on the map, right, divided by 5.4 inches. And this ratio of corresponding sides should be the same throughout, the similar figures here. And once again, I'll just do 800 over 8. I'll do the Chicago to New York corresponding sides, 800 miles to 8 inches on the map, or just 100 miles for 1 inch, right? So we have basically here y divided by 5.4 equals 100, right? 800 divided by 8. And then multiplying both sides by 5.4, we get y equals 540. Right? So back on the map here, this is 540 miles, right? The actual distance between Chicago and Memphis would be 540 miles. All right, pretty simple, that one, I feel. And every single one of these is very much the same. All right. Next question, example 5, will be, instead of Chicago, Memphis, and New York, now it's Atlanta, New Orleans, and Miami. And a very similar picture here, right? We have a map, a triangle. Now this is on a map, right? See, it's on the map. It's 2.1 inches from Atlanta to New Orleans, and 3.4 inches from New Orleans to Miami, and 3 inches from Atlanta to Miami. And we are told that the actual distance from Atlanta to New Orleans is 420 miles. All right. So let's, now I'm going to do this. I'm going to have the, now I'm just going to have the picture up. All right, and call this, exercise 279, example 5. Now in example 5, we are asked to find the actual distance from New Orleans to Miami. All right, now New Orleans to Miami, I don't know what that is. I'll call it X miles, right? I don't know how many miles is the actual distance from New Orleans to Miami. Now New Orleans to Miami, right, its corresponding length on the map is 3.4 inches. Let's put IN for inches now. And this should be equal to, the ratio of corresponding side lengths from, both. You could draw another triangle if you want, but now they told us from Atlanta to New Orleans, is 420 miles. And that should correspond to the distance from Atlanta to New Orleans on the map, which is 2.1 inches. Okay. Now again, corresponding units, numerator units, denominator units are the same. Now I'm just solving this this proportion. We have x over 3.4 equals, now 420 divided by 2.1. This is the same. If you multiply the numerator and denominator by 10, that'd be 4,200 divided by 21, which is 200. Right, because 21 goes into 42 twice. This is 200, and then I would just multiply both sides by 3.4. Now 3.4 times 2 would be 6.8, times 100 would be 680. Alright, so that this is 680 miles. Right, the actual distance from New Orleans to Miami. Right. Then example 6, the next exercise, exercise 280, same picture. Right, let me show you again. Same picture. I'll keep it up here. Now we want the actual distance from Atlanta to Miami, right? ATL to Miami. So once again, I don't know this, so I'll call it, X miles or Y miles or Z miles, whatever you want. Let's call it X again. And the ratio of that to the distance from Atlanta to Miami on the map is 3 inches. 3.0, but that's just 3 inches. And this should be equal to that same ratio as earlier. Right? I'll just use Atlanta to New Orleans again. the actual distance from Atlanta to New Orleans is 420 miles. And the distance from Atlanta to New Orleans on the map is 2.1 inches. I'm using that same ratio. So pulling this up. Now we're just solving this proportion. Now I told you already, right, this is, let's bring this over here, this would be x divided by 3 on the left equals, and we already said earlier, 420 divided by 2.1 is 200. And then multiplying by 3 gives me x equals 600. So the distance from Atlanta to Miami is 600 miles, right? X represented a number of miles. All right, and that's it. Simple enough. All right. Next question. All right. So now, example 7, be exercise 281, and I'll draw some pictures, right, to go along with these. And when I draw the pictures, hopefully you'll see the similar triangles, right? Triangles with the same angles, same shape, but different sizes. So we have a 2-foot tall dog casts a 3-foot shadow. At the same time, a cat casts a 1-foot shadow. How tall is the cat? So I'll draw some pictures here. Alright, so again we have this dog. Now I'm just going to put a vertical segment for dog. Alright, now that's a really good picture of a dog, right? Now this dog is 2 feet tall. 2-foot dog. Now it's casting a shadow, right? So the sun, here's the sun up by number 7 there, example 7. It's shining down on the dog and it casts a shadow on the ground. Let's say this is the ground here, and we form a nice little right triangle. Right? Doesn't matter really, that's a right triangle, just we get a triangle, right? The rays of the sun, here is the shadow on the ground. And they said the shadow is 3 feet long. Right? The dog casts a 3-foot shadow. Now, they said at the same time, meaning the sun is in the same position. So if a cat were standing near the dog, so here's the cat. Again, just a lovely drawing of a cat, just a stick. But if the cat were standing anywhere near the dog, and the sun was in the same position of the sky, when it casts a shadow, you'd get a similar triangle. These two triangles should be similar. These are similar triangles. So the dog triangle, it should be similar to the cat triangle. And again, the cat's shadow, they said the shadow of the cat was 1 foot long. And we are asked to find the height of the cat. How tall is the cat? So I'm going to call the cat's height, C feet. C for cat. And I set up a proportion. The height of the cat, C feet. Well, the cat corresponds to the dog, right? They're both this vertical segment. So the height of the dog was 2 feet. So we have C over 2, that ratio of corresponding sides, should be equal to the ratio of the only other sides I know. And again, I want the numerator to be from the cat triangle and the denominator to be from the dog triangle. That should be 1 over 3, right? The shadow corresponds to this shadow, 1 foot to 3 feet. And then I simply multiply by 2, and we get C equals 2/3. So in other words, the cat is 2/3 of a foot tall. Right? Or 8 inches tall. Right, if you want to put it in inches, but whatever. All right? That's it. Very simple stuff. So the next question I think is pretty similar about shadows. Right? Look at exercise 282. We have Larry and Tom were standing next to each other, right? So again, if you're standing near someone, if two things are near each other at the same time of day, the shadows they cast and themselves should be forming similar triangles, if they're standing straight up, of course. So Larry and Tom were standing next to each other in the backyard when Tom challenged Larry to guess how tall he was. Interesting challenge. Larry knew his own height was 6.5 feet. Right? And when they measured their shadows, Larry's shadow was 8 feet and Tom's was 7.75 feet long. So what is Tom's height? Right? So this is very similar to the dog and cat question. Just one question to go. So again, you got let's say the sun is here, shining down. And you've got Larry. Now Larry, it says Larry knew his own height was 6.5 feet. So 6.5 feet tall Larry is. And Larry, casts a shadow, the sun rays going down to the ground, casting a shadow on the ground. And Larry's shadow, they said, was 8 feet. And again, it should, standing straight up. And then Tom was, standing near Larry in the backyard. So again, standing straight up. And Tom, also cast some sort of shadow in the same direction there. And they said Tom's shadow was 7.75 or 7 3/4 feet long. And the question is, what is Tom's height? Now I'm just going to call it T for Tom. And these, since again they're standing next to each other, straight up, same time of day, these triangles should be similar. Right? This triangle and Larry's triangle should be similar to Tom's triangle. Now Tom and Larry are both the vertical sides, so they're corresponding sides. So we have Tom's height, T feet, divided by Larry's height, 6.5 feet. That ratio should be equal to the ratio of the lengths. The shadows are corresponding lengths. And again, I would like the numerator length to be from Tom's triangle and the denominator to be from Larry's. So numerator, Tom's shadow is 7.75 feet. And Larry's is 8. Okay. Now, me personally, I'm going to change all these stuff to fractions right now. So this is T over, now this is 6.5, that's 13 halves. Alright, 6.5 equals, this is 7 3/4, which would be, 7 3/4 would be 31 quarters. And then we're divided by 8. Alright, and then doing some simplifying over here. Now dividing by 8 is the same thing as multiplying by 1/8, or you can multiply the numerator and denominator of this by 4. That's 31 32nds. And then I would multiply both sides by 13 halves. Alright, that'll get rid of the 13 halves here and here. And I'll have Tom's height alone. Alright, so Tom's height is 31 times 13. Let's see, that'd be 310 plus 93. So that's 403 in the numerator and 64 in the denominator. And I'll punch this in a calculator. I guess I should have just done a calculator from the beginning, just taken this and multiplied by 6.5. So 7.75 divided by 8 times 6.5. Same thing as 403 divided by 64. So yeah, this is it's approximately 6.3 feet. All right. So Tom is about 6.3 feet tall. Because the answer here is actually 6.3 296875. Yuck. Right. So rounding that, I get 6.3 feet. Right. So Tom is approximately 6.3 feet tall. Right. So Tom is shorter. I mean, obviously, because he casts a shorter shadow as well, he's a little shorter than Larry. You know, they're standing near each other at the same time of day. All right, great. Next example. All right, more shadows. I think all of these are shadows. Shadow problems. Same kind of problem. So exercise 283. This will be example 9. The tower portion of a windmill is 212 feet tall. A 6-foot tall person standing next to the tower, again next to, right, at the same time of day, casts a 7-foot shadow. How long is the windmill's shadow? Alright, so once again the information here, and let's suppose the sun is up here by number 9. Got a windmill, alright, the windmill tower. Say this thing is 212 feet tall, and it casts some kind of a shadow. I don't know how far it's going, just making a triangle here, right? Just making a nice right triangle. Right. There's the windmill shadow. And then they said a 6-foot tall person who's 6 feet tall, standing near the windmill, but still in line with, is able to feel the sun, right? And actually cast a shadow. Well, the 6-foot person casts a shadow that is 7 feet long. So the shadow of the person is 7 feet. And once again, these objects are near each other at the same time of day, both standing straight up, I'm assuming. So they should be similar figures, these triangles. All right. And the question is, how long is the windmill shadow? So I'm going to call this S for shadow, right? The windmill shadow over here. And we set up the proportion of, the ratios of corresponding sides should be equal in similar figures. So S in the big triangle divided by the 7 feet, the shadow in the small triangle, should be equal to the ratio of the windmill's height to the person's height. Right, 212 feet to the 6 feet there. And this would reduce to 106 over 3 if you wanted. And then I would just simply multiply by 7. So S would be equal to, now if I multiply by 7, that'd be 742 in the numerator, divided by 3 in the denominator, which if you want, that'd be 6 and 7 is 13. So 3 goes into 7 twice, with 1 left over, then 14. 3 goes into 14 4 times, with 2 left over. And 3 goes into 22 7 times, with 1 left over. So this is 247 1/3 feet. Or, 247.3333333, if you wanted to round that, 247.3 feet, or 247 feet and 4 inches. However you want to put it, as long as it's correct, as long as it's equivalent to that amount of feet. Great. Very, very simple stuff. All right, and then finally, last question, one more shadow question here. Exercise 284. This will be example 10. The height of the Statue of Liberty is 305 feet. Nakia, who is standing next to the statue, again near the statue at the same time of day, both standing straight up. Right. So they'll cast similar shadows, they'll have similar figures. Cast a 6-foot shadow and she is 5 feet tall. How long should the shadow of the statue be? So this is almost exactly the same as the windmill problem, just with different numbers. So once again, just you don't have to draw the sun. I like just putting the sun up here, right, so I know where the shadows are going. Here's the statue. Here's the Statue of Liberty. This says 305 feet tall. Cast some shadow that I don't know the length of. So I'm going to call this, this shadow. I'm going to say this shadow has a length of s feet. Right? Don't know it. Let's say standing straight up. Then they say Nakia, this person. So here's Nakia's triangle. She is 5 feet tall and casts a shadow that is 6 feet long. How long should the shadow of the statue be? So see how it's almost basically the same picture as that windmill question from the last example. And I set up the following proportion. These are similar, right? Again, objects near each other at the same time of day, both standing at the same angle, standing straight up. Should be similar figures then. These two triangles should be similar. So their ratio of corresponding sides should always be the same. So s over 6 should be equal to 305 over 5. Now this is nice. This is 61. All right, 305 divided by 5 is 61. And then I would multiply by 6. We get s equals 6 times 60 is 366. And this is feet, right? And that was the length of the shadow of the statue. It would be 366 feet at that same time of day. All these problems are very similar though, right? Setting up a proportion, ratio equals ratio, making sure the numerators are coming from the same figure, the denominators are coming from the same figure, being consistent, and solving that proportion, and making sure it makes sense with the question, right? Actually answering the question. Great. Alright, so I'm hoping that watching me go through these 10 examples from this section here help you when you're working on similar problems. And thank you very much for watching.